Greetings and welcome to the Chemistry 151 Chemical Models Lab. This is a great lab to see how chemists can figure out how electrons are arranged around atoms. And at first that may not seem like such a big deal, but it can lead to some really interesting changes to structure. So sometimes you'll think that structures would be flat and they're actually three-dimensional, and sometimes the opposite too. You can also use these skills to figure out when molecules will react or when they won't react, as it turns out. This is a pretty powerful part of organic chemistry, biochemistry, medicine, and lots of other areas. So this will be a great insight as to how this works. Let's get started. Chemical models involve what's called a Lewis structure. Lewis structures are named after an American chemist named G.N. Lewis, who kind of formulated these ideas. And basically, Lewis saw that, you can think about electrons as being placed around a central atom in a molecule. And around that central molecule, you're going to have all the kind of things we've seen so far. So, for example, and what's really important here, electrons, when they get close to each other, they start to repel. And that repulsion is actually the key to understanding this whole lab, to be totally honest. So once you understand how electrons are placed around atoms, you'll get insights into their geometry, i.e. what they look like in 3 dimensions. You'll see more information about what their bond angles look like, and also something called polarity, which we'll talk about. Now, all of this is possible through an extension of Lewis structures called valence shell electron pair repulsion theory. That's way too many words, so chemists abbreviate it as VSEPR a lot, which is fantastic, and that's what I would expect you to know. I'll never test you on what that VSEPR means. But anyway, VSEPR basically is a set of formulated rules as to what happens when electrons get too close to each other, and it does result in the structures you see. So in this lab, you're going to gain experience drawing Lewis structures and then interpreting the structures using VSEPR. And from VSEPR, you can figure out bond angles and stuff like that. And these rules are pretty profound. You'll be looking at molecules maybe later in biology, or maybe you'll see a pharmaceutical medicine where the structure is listed, and you can actually apply these rules. Pretty cool stuff, at least in my opinion. To draw a Lewis structure, there's a couple of things you need to go through, and I'm hoping you've seen some of this before, but if you haven't, here's kind of a quick and dirty overview of the rules. First of all, when you have a structure, you need to decide what the central atom is. The central atom in a molecule will always be the atom which is less into electrons, i.e. lowest electronegativity. Electronegativity is something we'll talk about later, but for right now, just think about it. The central atom is always going to be the atom which is less into electrons than the other atoms. Now, the central atom can never be hydrogen. Hydrogen only has one electron, and it's not sophisticated enough to handle more than one bond. So we're going to see that hydrogen is never going to be the central atom. It's always on the outside or a terminal atom. Usually, the central atom is the first atom listed in the formula. So as an example of this, ammonia is NH3. The nitrogen will be the central atom. And methane is CH4. The carbon, the first atom listed, is going to be the central atom. Next thing you want to do is count the valence electrons and find the electron pairs. Now, valence electrons are related to the group number of the atom. And in the lower left corner right there, you can see I've got 1A, 3A, 4A, etc. like that. Everything in group 4A, carbon, which is listed there, silicon right below it, as well as germanium, those kind of things, are all going to have 4 valence electrons because they're in group 4A. And under group 7A, on the right side there, you can see there's fluorine, chlorine, bromine would be under it, and iodine. All of those will have 7 valence electrons because they're in group 7A. So the group number literally is the valence electrons. Valence electrons are the electrons which will react in a molecule. So as an example of that, fluorine actually has a total of 9 electrons, if you remember back to the atomic number. The 7 electrons, which are valence electrons, are the ones which will react to make molecules. The other 2 electrons, i.e. 9 total electrons in fluorine minus 7 valence electrons, those other 2 electrons are called core electrons, and they just kind of sit there and don't do anything. They're too close to the nucleus to be able to make bonding molecules. So you want to count up all the valence electrons and then divide that number by 2 to find the electron pairs. We're going to be making pairs in our molecules to make bonds with other atoms, and sometimes the lone pairs will be on the atom by itself. We'll see this here in a little bit. Now, if you have any left over and stuff, then you can start putting them as lone pairs, and you can also create what's called pi bonds around them to create lone pairs. Lone pairs sometimes can be used to make multiple bonds around them. I'll show you an example at the end of this video of how that works. A pi bond is also known as a double bond if there's one extra bond or one extra pi bond, or a triple bond if there's two extra pi bonds, which we'll see in other higher level chemistry courses. But for right now, this gives you like a rough overview as to how this works, and we'll see some examples here in a little bit. Now, VSEPR, valence shell electron pair repulsion theory, is actually pretty chill to use. You just have to realize how many clouds of electrons there are around the central atom. Now, a cloud in this concept can be a bond to another atom, i.e. a single bond, which will be very common, double bonds, which we'll see once in a while. Triple bonds do exist. We won't see them so much here, but they do exist. But a lone pair also counts as a cloud, and each of those is just a big shimmering little area of negative energy, and they want to be as far apart from the other little shimmering bundles of negative energy as possible. Remember, electrons and electrons repel each other, and that's what's happening here just in the molecule. If you have a double or a triple bond, it counts as one cloud. We'll talk about that here in a little bit. Now, in the lab itself, you have the table, which is shown there in the lower left. And what it does is it shows on the far left side the number of total electron clouds. And then you need to know, to figure this out, how many clouds are connected to atoms, i.e. atom clouds, and how many clouds are connected to just one single atom, which are called lone pair clouds. And from this information, you can get the electron pair geometry, EPG, which is going to be super helpful to us in a little bit. You can also find the molecular geometry, MG, which is what the molecule, quote unquote, looks like if the lone pairs are invisible, and this can be helpful to chemists too. In addition, you'll be able to find the bond angles within the molecule, which can be really, really helpful. Here's an example of NH3, ammonia's Lewis structure. And if you look there in the central N, nitrogen is the central atom, all right? And around that central atom, we have 1, 2, 3 pairs of electrons. Those lines represent pairs of electrons connected to other atoms. So that would be 3 atom clouds in this table right there. But you also have on the top of the nitrogen, right there on top in purple, you have 1 lone pair cloud. So we would say that the nitrogen in NH3 has a total of 4 electron clouds, 3 of which are connected to atoms, and 1 is connected to just itself. It's a lone pair cloud. So if you look down here then on the bottom, you'll see that there's 4 electron clouds there towards the bottom. 3 of them are connected to the atom clouds, 1's connected to a lone pair cloud. So this thing would have a tetrahedral electron pair geometry. The molecular geometry is trigonal pyramid. That's just a name you can know. Don't have to worry about what it means. And you can even find the bond angle. The bond angle here would be 109 degrees. So this is how this works out. It's pretty chill once you get used to it, of course, but of course interpreting it first can be a little bit weird. The final thing you're going to think about is if a molecule is polar or nonpolar, all right? And polar and nonpolar represents how electrons are displaced in the molecule. And the best real-world analogy that I know of is if you have a piece of bread and you want to spread peanut butter across the bread. If you spread the peanut butter evenly across the bread, that would be a symmetric distribution of peanut butter. So every bite has the same amount of peanut butter. That would be a non-polar peanut butter distribution. Now, electrons, unfortunately, you can't eat like peanut butter, which is one of my favorite foods, by the way, but that's beside the point. But if electrons are distributed evenly amongst the molecule, then you have a non-polar molecule. And if a molecule wanted to take a bite of that non-polar molecule, it would have the same number of electrons on the left as it does the right, or the top, or the bottom. Polar means that you have an unequal distribution of electrons. So let's go back to the silly bread and peanut butter idea. Sometimes when I'm lazy, I just put peanut butter on one side. I don't feel like spreading it. So if I bite on that side of the bread, wow, I get a lot of peanut butter. But if I take a bite on the other side of the bread, I don't have any peanut butter or hardly any peanut butter at all. That's an example of a polar distribution. You have an unequal distribution of electrons. It's an asymmetric distribution. Now again, we're not talking about peanut butter, darn it, but we're talking about electrons. Electrons are usually asymmetrically distributed, which means that maybe one side has more electrons than the other side. So a molecule takes a bite of something, it'll have more electrons on one side than the other. So let's look at the examples there on the left-hand side, CH4, CH2Cl2, and CCl4, and their Lewis structures are there on the left-hand side. You can see that both with CH4 and the bottom CCl4, the molecule is completely distributed by the same kind of atom. So in the top part, carbon is completely surrounded by hydrogens, and each hydrogen has so much electrons, but they're all hydrogens. That would be an example of a symmetric molecule. Every bite you take of a CH4 would have the same amount of electrons on each side. The hydrogen-carbon bond is the same all the way around. And the same for the bottom molecule, CCl4. Chlorine actually has a lot of electrons around it, but each carbon bond is connected to a chlorine, so each of them would have the same amount of electrons all the way through. The middle molecule, however, has 2 Cl's and 2 H's. Now, chlorine, we're going to see later, has a lot of electrons on it, so that's going to have more electrons, more peanut butter, if you will. Hydrogen doesn't have that much on it. So if a molecule was going to look at this molecule, it would see a lot of electrons where the chlorines are, not of a lot of electron density where the hydrogens are. And this leads to polarity. And polarity is a really interesting kind of concept when it comes to science, and you'll see more about this later. But for right now, the really important thing is that if the molecule is completely surrounded by the same kind of atoms, so for example, the carbon in CH4 completely surrounded by hydrogen, or the carbon in the bottom example completely surrounded by chlorines, those are symmetric and those are non-polar. They're going to have the same amount of electrons and stuff all the way around it. Those are symmetric molecules. On the other hand, you can see in the middle here, you've got chlorines, and those lone pairs, those dots, those are lone pair electrons. That's a lot of electron density. And the hydrogens on the left and kind of down parts right there, they don't have the electrons that the chlorines have. So this leads to polarity then. This is a polar molecule. Now, we're not going to do as much with polar and non-polar as we totally could, but the important part is that if you have to guess, honestly, more molecules are polar than non-polar, all right? You can always tell by this symmetry. If everything around the central atom is the same, like the top and the bottom examples, they will be non-polar. But almost all the molecules we look at will have some kind of asymmetric, like you'll have a chlorine, a bromine, and a silicon or something around your carbon. That would be an asymmetric distribution. You don't have the same kind of atoms. So if you don't have the same kind of atoms all the way around the molecule, you can basically assume it's going to be polar. So at this point, let's do some examples. I'm going to do 3 examples of Lewis structures and how to interpret it using VSEPR geometry and that sheet, and we'll also talk about polarity and stuff like that. So first we're going to look at CH4, which is methane. Now carbon is listed first, and so almost always the first atom listed is the central atom, which is the first thing you need to do. Another way to verify that is hydrogen can never be the central atom. So in this case, definitely carbon's going to be the central atom. Once you figure out the central atom, the next thing you need to do is figure out the number of valence electrons. And if you look on a periodic table, carbon is in group 4A, so that means it has 4 valence electrons. Hydrogen is in group 1A, so hydrogen has 1 valence electrons. But you can see there that there are 4 hydrogens, so I'm going to multiply that 1 by 4. So 4 plus 4 equals 8. This molecule, CH4, has 8 valence electrons, 8 VE. And those are all the electrons that are going to be used to bond in this molecule. Now, as we talked about earlier, in these kind of molecules, we worry about pairs of electrons. So almost always what I do is I divide the valence electrons by 2 to find out the number of pairs that are going to be in the molecule. Pairs can be lone pairs on just a single atom, or they can be bonding pairs when they're connected to an outer atom. But we only have 4 pairs to deal with in CH4, and that'll be important. Okay, so now I know the central atom's going to be carbon. I know we have 4 pairs total. What I'm going to do is I'm just going to draw carbon with 4 hydrogens around it like that. And you need to connect those outer atoms to the carbon because you don't want the hydrogens to run away. So I'm going to use what's called a bonding pair or a sigma bond, depending on who you're talking to. And you can think about that as like a little chain that just connects the outer atoms to the inner atoms. I'm connecting the outer hydrogens to the carbon so they won't go running away. Now, each one of those little lines I just drew is a pair of electrons. So at this point, I don't have any more pairs of electrons to put in there. So I've used up all the glue I have. At this point, it is helpful to think about if everything is happy. Carbon has what's called an octet. Octet means it has 4 pairs of electrons around it, and basically for us, anything but hydrogen needs 4 pairs. And that carbon does have it. It has 1, 2, 3, 4 bonding pairs, 4 lines connecting the hydrogens to it. So carbon actually has an octet. Hydrogen only needs 1 pair to make it happy. So this right here is actually the Lewis structure for CH4. I've distributed all of my electron pairs, carbon's in the middle, hydrogen's on the outside, stuff like that. Now, if you look at this molecule, carbon has, as we talked about earlier, 1, 2, 3, 4 pairs of electrons around it. 4 clouds of electrons. And all of those clouds are connected to atoms. They're not connected to just carbon. They're all connected to atoms. So if you look back on that table under 4 clouds total, 4 atom clouds and 0 lone pair clouds, you'll find that the EPG for this is tetrahedral. A lot of times I abbreviate this tetra when I'm lazy. Oh, did I say that? Is this? Oh, I should. Yeah, anyway, do as I say, not as I do. No. Anyway, electron pair geometry officially known as tetrahedral. And if you look on that same row right there, under molecular geometry, it is also tetrahedral. Same EPG and MG name. And then also in that same column, you can see that the bond angle is 109 degrees. If you're a math person in a tetrahedron, it's actually 109.5. I don't mind if you write that. 109 works fine for us here. And the last part of these questions is that once you know if it's polar or nonpolar. Now, if you look at this molecule, everything around that central atom is nothing but hydrogens. You've got no silicon atoms connected to carbon. You have no chlorines. You have no lone pairs. So this is a symmetric molecule. Everything's the same all the way around it. This is actually a non-polar molecule. So what I've done here is I've drawn the Lewis structure, the CH4. You don't have to circle the lone pairs or the bonding pairs like I have. The EPG is tetrahedral. The bond angle is 109. The MG is tetrahedral. I forgot to mention that. And the molecule is non-polar. It's symmetric because everything around it is the same. Now, my drawings definitely leave something to be desired. So this is a little bit fancier version using computer-generated things. You can see what I did there. I found the central atom was carbon because it was listed first. I counted the number of valence electrons. Carbon was group 4, so 4 valence. Hydrogen group 1, so 1 valence, but there's 4 of them. That's a total of 8 valence electrons. Divide that number by 2, 4 pairs of electrons. Then I started placing lone pairs or sigma bonds between the outer atoms and the middle one to connect them. That actually took all 4 pairs. I didn't have anything left for lone pairs or stuff like that, which we'll talk about in the next example. So CH4 there in the top middle, or the middle left, I guess, is actually the Lewis structure for CH4. And then when we interpret this, there are 4 clouds around the carbon. Those 4 bonds to hydrogen, those are each called a bonding cloud. cloud. And there are no lone pair clouds, i.e. the carbon doesn't have any lone pairs. So if you look in that thing, its EPG is tetrahedral, the MG is tetrahedral, MG molecular geometry, EPG electron pair geometry. The bond angle is 109, and as we talked about, the molecule is symmetric. Everything around the carbon is hydrogen. There's no chlorines or bromines or anything like that. So this is a non-polar molecule. Pat yourself on the back. Lewis structure number 1 down, taken care of. Let's look at another example. In this example, we're going to look at carbon tetrafluoride, CF4. It's an interesting molecule with lots of interesting uses, but we're going to then see how to draw the Lewis structure, interpret it, and stuff like that. Now, just like last time, we need to figure out what the central atom is, and it's almost always the first atom listed, carbon once again. We're going to see carbon likes to be in the middle of molecules. There's other atoms that can be in the middle too, but carbon is a real good example. So carbon's going to be in the middle, and once you figure that out, we need to figure out valence electrons. Well, carbon is still in group 4, so that means it has 4 valence electrons. Now, fluorine is in group 7. It's right on the edge there next to the noble gases. So each fluorine has 7 valence electrons, and there are 4 of them. So total valence electrons here, 4 plus 28, that would be 32 valence electrons, VEs. I'm going to divide this by 2. That means there are 16 pairs of electrons to place around this molecule. So a few more electrons than we had in the last example. Now to draw the Lewis structure, I'm going to put the carbon in the middle of the 4 chlorines. 1, 2, 3, 4. Like before, I'm going to connect the outer atoms to the inner atoms using a single or sigma bond. So each of those lines I drew there is a bonding pair, and I have 16 pairs total, and I've just used 4 of them up. That means I have 12 pairs left. Now, CF4 is different than CH4 because hydrogen only needs 1 pair to be happy. But fluorine, like most of the atoms on the periodic table, needs an octet, which means 4 pairs around it. Now, each of these fluorines right now has just 1 pair, 1 bonding pair to carbon. So what I'm going to do now is put lone pairs on the outer atoms first, and if there's any left over, I'll put them on the middle atom. Fluorine on the outside here needs 1, 2, 3 lone pairs to make it happy. And if you think about it then, the fluorine there I just drew has 1, 2, 3 lone pairs and 1 bonding pair, 4 pairs total. That's the octet. Now I did use up 3 pairs, so I have 9 pairs now left to go, but as you can probably see, I have 3 more fluorines. So what I'm going to do now is I'm going to put 3 pairs, 3 lone pairs, on each of those fluorines. There. 3 pairs on each of the 3 fluorines. That's 9 more pairs I put in. I've now used up all of my lone pairs. I don't have any more pairs, any more glue to put around the molecule. So this is the Lewis structure now for CF4. And it's interesting. You can see how the fluorines have a lot more electrons around them than hydrogen. Fluorine is a powerhouse when it comes to electron density, and fluorine loves to have electrons, so that's why it has the lone pairs, and carbon has just 4. Okay, so this is the Lewis structure. We can now interpret this in terms of VSEPR geometry, looking at the clouds around the central atom. And again, that central atom is the carbon. So carbon has, I'll circle them here again, 1, 2, 3, 4 pairs of electrons, 4 clouds, all right, 4 clouds, and all 4 clouds are atom clouds. Carbon does not have any lone pairs on it. The fluorines do, they got tons of them, but the carbon has just 4, so 0 electron pair clouds. So what this means, if you look at the table, is the electron pair geometry here, tetrahedral. And the molecular geometry, if you look on that same table, is also tetrahedral. Again, my handwriting is really bad, and it's even worse on the iPad, so I apologize for that. But you can keep going. The bond angle for these kind of molecules, 109 degrees. All right, 109.5 is fine if you're a math person. And then finally, because the carbon is surrounded by 4 fluorines, it's another symmetric molecule, all right? There's no carbons connected to chlorines on there. It's all fluorine. So the peanut butter distribution, which I should really call electron cloud density, the electrons are distributed evenly on that whole molecule. You've got fluorines in each direction. So this is another example of a non-polar molecule, all right? So, woohoo! All right, here's another Lewis structure, CF4. CF4 had a lot more electrons around it than CH4 did, but it's the same kind of geometry, all right? Different sets of electrons, but same idea. Now, my handwriting is obviously atrocious. Here are some better examples using computer-generated things. It shows there how carbon, once again, central atom. We counted the valence electrons. Carbon is 4, fluorine is 7, and there's 4 of them. So 32 valence electrons, 16 pairs. Put carbon in the middle, fluorines are on the outside. Connect the outer atoms to the inner atom using a lone pair or sigma bond. That's the single bonds. We then put lone pairs around the outer atoms first, and if there's any left over, we put them on the inside. But because fluorine likes to have the octet, which is basically 4 pairs of electrons, fluorine is happy with 3 lone pairs and a bonding pair. And when you do this to all 4 of the atoms, it used up all of our pairs, so we're all good to go there. Carbon has an octet. Notice it has 1, 2, 3, 4 bonds to other fluorine atoms. So carbon also has an octet. Everything has an octet here. Everything is totally happy. Now in the molecule itself, carbon has 1, 2, 3, 4 clouds, all atom clouds once again. So big surprise, electron pair geometry is still tetrahedral. Molecular geometry is also tetrahedral. 109 is the bond angle. And because the structure is completely the same all the way around the carbon, it's going to be a non-polar molecule, just like CH4 was. So there are some similarities between CF4 and CH4, definitely, also some differences, but this is where these Lewis structures and VSEPR can really come in handy. So CF4 and CH4 have very similar properties in some levels. There's some differences too. Fluorine's electrons makes for some very interesting reactivity, but you at least get the idea of what's going on. In this last example, we're going to look at a compound called formaldehyde, and formaldehyde has the structure CH2O. Formaldehyde is very interesting. It's used a lot in the funeral services area for preserving dead bodies and stuff like that. They place formaldehyde and water into it, making a solution called formalin. That's neither here nor there, but it is pretty interesting. So let's say that you were interested in what does the structure look like of formaldehyde, Dr. Russell? Well, great question, random student who's watching my video. Anyway, formaldehyde is CH2O, so like we've seen before, central atom is going to be carbon. First atom listed, almost always the first one listed. Second thing, let's count valence electrons. Carbon is in group 4, so it has 4 valence electrons. Hydrogen is in group 1, and there's 2 of them. And oxygen, if you look on the periodic table, is in group 6. So total valence electrons, 4 plus 2 plus 6, that would be 12 valence electrons. We'll divide that by 2 to find the pairs. There's going to be 6 pairs of electrons, all right? My handwriting's really sloppy, sorry about that. Anyway, next thing, like before, carbon goes in the middle. You can put the atoms around anywhere you want. I'll put the hydrogens on the left and the right and the oxygen above. It doesn't really matter. You could have the oxygen below, you could have the oxygen to the right or the left. It doesn't really matter. We're just trying to see where the electrons go. Now, like before, connect the outer atoms to the inner atom using a lone pair. So we're going to make bonding pairs from the outer atoms to the carbon to keep them kind of connected. That uses up 3 of our pairs. We've got 3 more left to go. Now here's where it gets interesting in this molecule. You need to put the remaining lone pairs on the outside atoms first to give them an octet like we did with fluorine, and if there's any left over, put them on the inside. So for this molecule, what that means is we're going to make 1, 2, 3 lone pairs around that oxygen, and that gives oxygen an octet. If you look at that oxygen, there's 1 lone pair or 1 bonding pair to carbon and 3 lone pairs, 4 pairs total. So oxygen here is happy, and I've used up all my pairs. Now, hydrogen is happy. Hydrogen only needs 1 pair. It's pretty chill. Doesn't need it. But good old carbon there, carbon also needs to have an octet. And in the last 2 examples, carbon naturally had 4 bonding pairs to either hydrogen or fluorine, so this wasn't a problem. But you can see right now this carbon only has 3 pairs around it, 3 bonding pairs. So if you get to this situation, what happens is oxygen has to start sharing its outer electrons, its outer lone pair electrons, and make another bond with carbon. So what I'm going to do here is I'm going to essentially erase this pair of lone pairs, and I'm going to put that pair and make a second bond to carbon. Now this is the first example we've seen of what's called a pi bond. Sigma bonds are the first line you draw from the outer atoms to the central atom. But if you draw 1 or even 2 other bonds from the outer atom to the central atom, which we've just done with oxygen, this is called a pi bond. So the blue bond there that I just drew, that's a pi bond. That's the symbol for pi. And the red one I drew initially, that's a sigma bond. If you have a sigma and a pi bond, it's called a double bond. So this carbon-oxygen molecule has a double bond around it, all right? And why that's kind of cool here is because, let me use even another color, is that your oxygen still has 1, 2, 3, 4 bonds, all right? It has 2 bonding pairs to carbon and 2 lone pairs. 2 plus 2 is 4. That's the octet. And the carbon is also happy. It is sharing the 2 bonding pairs to oxygen, and it also has those 2 pairs right there. So it also has a total of 4 bonding pairs. It has the octet as well. Everybody's happy and everybody's cool here. Now, let me erase some of these bonds I've just drawn because it's kind of messy. Carbon has a double bond to oxygen. It has 2 single bonds to hydrogen, and that would be the Lewis structure for the molecule, all right? Kind of cool. Now, once we have this molecule, and you know what, maybe I should draw it down here again because that's kind of messy. There we go, C double bond O, H, H, da, 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 da. All right, once you have this molecule, you can do the same thing for Vesper. You just need to figure out how many pairs are connected to the central atom and all that jazz. So around the carbon, the central atom, there's 1 bonding pair to another atom there. There's 1 bonding pair to this other hydrogen right there, and the double bond. Now here's the thing, double bonds and even triple bonds, if you see them, count as 1 cloud. And we'll talk about this in a future course in more detail. But we would say here for carbon in this molecule that there are a total of 3 electron clouds. The double bond counts as 1 big cloud. Now, all 3 of these electron clouds are connected to atoms. So these are 3 atom clouds, and there are 0 lone pair clouds. So if you look on that little table in our lab then, 3 electron clouds that are all atom clouds, the EPG will be what's called trigonal planar. Trigonal planar is kind of like a triangle and stuff like that. It's a little different geometry here. There are no lone pairs on the carbon, so the Mg will also be trigonal planar. The bond angle will be 120 degrees if you look under trigonal planar. And this molecule finally does not have a symmetric distribution of atoms. It has 2 hydrogens and an oxygen. And the oxygen has a lot more electron density on it than the hydrogen does. So this is an asymmetric molecule. You have different amounts of electrons towards the oxygen than you do the hydrogens. So we would call this molecule polar. All right. Honestly, most molecules are polar. We've seen a couple of non-polars here because they're great teaching examples, I won't lie. But this one is definitely polar. Not everything around the carbon is the same. Like if carbon had just hydrogens around it, it would be non-polar. If carbon had just oxygens around it, it would be non-polar. But this molecule has both hydrogen and oxygen. Those are different. This molecule is going to be polar. My drawings are pretty sloppy, and you can tell I'm kind of all over the place. Writing on an iPad has never been my forte. So here's a better example as to what's going on. So in formaldehyde, carbon is the central atom. When you count the valence electrons, carbon is 4, hydrogen's 1, and there's 2 of them. And you add the 6 from the oxygen, that gives to a total of 12 valence electrons, or 6 pairs. So you want to put carbon in the middle, the other atoms around the outside. You start with a single bond to the hydrogens and a single bond to the oxygen. If you have any pairs left over, and you do, you put them on the outside atoms first, and then the inside atoms get them later. So as we saw in the last example, oxygen initially had 3 lone pairs around it. We had to share one of those pairs, though, with carbon, because carbon also needs to have an octet, i.e. 4 pairs. So that carbon has 1, 2, 3, 4 bonds around it. It's totally happy, 4 pairs of electrons. But oxygen also has 4 pairs. It has 2 pairs to the atom carbon, 2 bonding pairs, and it has 2 lone pairs on it exclusively, so everybody's happy. Remember, hydrogen's happy with just 1. Now, for the electron pair geometry, carbon has 3 clouds around it. Double bonds and triple bonds count as 1 cloud, just like single bonds. So we would say the carbon has 2 clouds, 1 to each hydrogen, and 1 cloud to the oxygen, even though it's a double bond, so 3 clouds total. This is the trigonal planar electron pair geometry. The molecular geometry is also trigonal planar. Angle for a trigonal planar system is 120 degrees. You can see that that structure tries to represent like kind of 120. A full circle is 360. And finally, this molecule is polar. Not everything around the carbon is the same. You've got oxygen on one side and hydrogens on the other. If you had just hydrogen around carbon, it would be nonpolar. If you had just oxygen around carbon, it would be nonpolar. But this is a mixture now of hydrogen and oxygen. It's going to be a polar molecule. Okay, that totally gets you started with this lab. Now it's time to just practice a little bit and see how this goes with Lewis structures. Once you get the hang of this, it's not too bad, and you'll see some of these structures kind of repeat. If I can help in any way, please reach out to me, contact me, or talk to the LSC Avid Center. They can help out as well. All right, good luck with your Lewis structures. I'm rooting for you. Have a great day.